Hi everyone, in this tutorial what we are going to do is really quickly summarize stereocenters again and then progress into a set looking at counting total asymmetric centers versus total stereocenters. Stereocenters, recall, are carbons at which the interchange of two atoms or groups could result in the formation of a new stereoisomer. These types of stereocenters include asymmetric centers, sp3 carbons bonded to four distinct atoms or groups. We classify those with the distinction of R and S, are absolute configurations. Again, we'll talk about how to classify those soon. We have the carbons of cycloalkane rings, the sp3 carbons, where we see cis-trans stereocenters. Those are not asymmetric centers, but we do see the cis-trans isomerization. And then we also have EZ stereocenters, where we have the sp2 carbons of double bonds that could be classified as E or Z. Okay. Now, in each of these examples, we are going to count the number of total asymmetric centers and the total number of stereocenters. We will first count the asymmetric centers and then the stereocenters. I find that to be a good way to do this. So if I'm going too quickly, just pause the video and count on your own, okay? I apologize if I go too quickly. We have 1, 2 asymmetric centers in this molecule, 2 asymmetric centers. Let's count the total number of stereocenters. We now still count the asymmetric centers, but now we look for cis-trans stereocenters or EZ stereocenters. We now have 3 and 4 total stereocenters. This double bond could be classified as E or Z, and therefore each of those carbons are considered stereocenters. Remember, if a double bond is within a ring size 3 through 7, we cannot classify that as E or Z, and therefore those are not considered to be stereocenters. 2 asymmetric centers, but 4 total stereocenters. Number 2, let's first identify asymmetric centers. We have 1 asymmetric center here, and then we look for the total number of stereocenters, still count the asymmetric center first, and we see a double bond here and a double bond here. The double bond within the 6-membered ring cannot be E or Z, therefore those carbons of the double bond are not stereocenters. But notice how this one is not fully in the ring. Both of the carbons of the double bond are not in the ring. Here, because this carbon has 2 distinct groups, and this group is different from that group, if you were to draw a line here, we see a difference, right, in the connectivity of the groups. Therefore, this is an EZ double bond. So we're going to say, yes, this could be considered an EZ double bond. It can be exo to the ring, meaning outside of as opposed to endo. And both of those carbons would be considered to be stereocenters. So we have a total of 3 stereocenters in this molecule. Let's now do number 3 together. We are going to have 1, 2, 3, 4 asymmetric centers. 4 asymmetric centers. We count those as also being possible stereocenters. Now we look for cis-trans and EZ stereocenters. This double bond is exo to the ring, but notice how there are 2 hydrogens. So this is not an EZ double bond, therefore we cannot count those 2 carbons as possible stereocenters. We do have now 5, 6, 7, and 8 total stereocenters. Each of these double bonds here are considered EZ double bonds, and therefore both of the carbons of the double bond, this one, this one, this one, and this one, are stereocenters. Okay, let's now look at kind of a challenging one, number 6. Don't let molecular complexity scare you. Still dive into it and process it visually one component at a time. Let's count the asymmetric centers. We have 1, 2, 3, 4 asymmetric centers. We might look at these 2 and wonder, are they asymmetric? And the answer is no. Because as you start here and you go around, we start to see that there is symmetry about the ring structure. So those are not asymmetric centers. Okay. Now we're going to look for cis-trans stereocenters and EZ stereocenters. We have a total of 4 asymmetric. We'll also count those as being stereocenters. Now we identify any double bonds and wonder, are they EZ? Here we have hydrogen in this group, hydrogen and chlorine, 2 distinct groups on either side. That is an EZ double bond, therefore we will count 5 and 6. Here we have 7 and 8, 9 and 10, and there are 10 total in this molecule. While these are not asymmetric centers of the ring, the ones I labeled as 9 and 10, they are cis-trans stereocenters, where we can see this cis-trans isomerism about this 1,4 substituted ring. This double bond on the far side of the molecule on the right has two of the same groups, methyl groups, on that carbon. Therefore, this double bond could not be classified as E or Z. Okay, so I want you to go through the rest of this set and practice identifying stereocenters versus asymmetric centers. Understand that all asymmetric centers are stereocenters, but there are certain stereocenters that are not asymmetric centers, and those are your cis-trans stereocenters or your EZ stereocenters of EZ double bonds.